First of all, my name is Heiko Seitz, and I am Product Marketing Manager at IDS. In my presentation, I would like to talk about the interface that basically all industrial cameras have in common. This concerns the electrical inputs and outputs, such as flash, trigger, and GPIOs. However, we will see that within different camera models, they provide a very different behavior and even different operation modes, which in turn can have serious impact on your application. But before we get started, a few words about IDS as camera manufacturer. IDS is one of the world's leading manufacturers of digital industrial cameras based in southern Germany and employing around 350 people. Since 1997, we develop and manufacture components for industrial imaging processing, exclusively at our site in Obersulm near Heilbronn, which we distribute internationally and which are used in many different industries. So coming to the topic, the I/O system is an automation interface between industrial cameras and, for example, a production plant. It enables the exchange of electrical signals that are essential for automated image generation or processing. The camera receives trigger signals via digital inputs to capture images or videos at the right moment. Digital inputs or outputs, control lighting, other cameras, or return status information to a system. These signals thus ensure synchronization between cameras, lighting, motion sequences, and without a precise I/O communication, reliable integration into automated processes is not possible. The specification and capabilities of the camera I/Os systems determine how accurately a camera responds to an external event. And this applies not only to the group of 2D standard vision cameras, monitoring cameras with streaming and recording functions, 3D cameras, intelligent AI cameras, or cameras with also event-based sensors also have these I/O signal systems. In this presentation, I will get you a brief overview of how this I/O functionality of these different industrial camera categories works and how familiar terms such as flash and trigger often only reflect only a part of their functional capabilities, as we will see in a moment. Via the I/O connectors and the underlying electronics, cameras exchange the electrical signals with the outside world. Today, the pins are used very generally in all camera categories and are usually labeled line 1, 2, 3. To be very general, the pin electronics determine which feature and capability lines provide electrically. This includes whether they can be inputs, outputs, or even be configurable in direction. The electronic also differ in terms of whether, for example, optoelectronic decoupling is integrated to protect the internal electronics of a camera. If a differential signal with a higher voltage is used to optimize the signal quality, or if you want to use direct wiring with a 5-volt TTL level for a signal exchange. All of these circuit variants have their advantages and drawbacks in terms of signal delay, protective circuitry, shielding, robustness, latency, or functionality. For camera series that do not have additional I2C connectors, such as our cost-optimized X-series cameras, the GPIO pins can also be configured as a UART interface via software and then used to communicate with other devices. There is also a recent how-to video on our Vision channel if you want to have a look at this. Okay. So after the electronics, let's now take a look at the real functions of these signals. Because how highly flexibly the I/O electronics of a camera can be used today can be seen here in the example of a 2D standard vision camera. The outputs are not only used to control lighting, they can address external devices such as PLCs, robots, sensors, or even synchronize other cameras. In addition, the signal, the exact timing of internal camera events, such as the start of image capture when sensor data is read out, a pulse width modulated signal, and much more status information. The inputs are also highly flexible and versatile, just like the outputs, and can be controlled by various sources such as light barriers, PLCs, encoders, or sensors. All these external triggers events can then be used to initiate various actions in the camera. For example, the capturing single or multiple images, reading sensor data from internal memory, or exposing individual lines in a possible line scan mode. However, since GenyCam and SFNC triggering an image capture is no longer limited to one external source, by separating the hardware device inputs from the triggered software functions in the camera, electrical input signals become an abstract signal definition with a wide range of use. Counters, timers, generated pulse width modulated signals, or software even are possible signal generators. Especially in the standard vision camera environment, users have access to a very versatile Lego-like trigger logic that enables highly flexibly interconnection of internal and external signal sources, ideal for demanding applications with high requirements for timing and automation. In many use cases, the speed or latency of the triggering signal, in other words, the timing until the finishing of an image capture is produced, or even the precise timing with the flash, is very important. Here are four very common examples of how users can apply the trigger and I/O logic of standard vision cameras. The first example above is probably the best known case. A non-cyclic imaging acquisition where an external signal source and components on a conveyor belt with varying distances produce a non-cyclic trigger signal that are intended to immediately trigger the exposure of the sensor. In the second case, the duration of the electrical signal edge even determines the length of the exposure time for the sensor. In case 3, an additional trigger delay is used to adjust the coordination between trigger signal and conveyor belt speed, for example. And by using a counter, it's also possible that a fast image sequence can be recorded by a trigger signal. If you would like to learn more about the many different applications of trigger I/O systems with 2D industrial cameras from IDS, I recommend our how-to section in Vision Channel, where we have several videos and hands-on demonstrations on the topic of triggering. It's really worth taking a look. But in applications where a precise timing of I/O system is critical, delays, jitter, and other latencies that can be caused by hardware and software should also be taken into account. The I/O electronics alone can cause a delay in a trigger signal, for example, due to an optocoupler. We measure the switching times for each model hardware platform, and at ambient temperature and 24 volts voltage, they range between approximately 100 and 160 nanoseconds. The signal processing time in a chip can also differ. In FPGAs, for example, the delays are well below 1 microsecond, whereas in an USB controller, interrupt routines can take up to 25 microseconds. So depending on the sensor and time until the pixel exposure starts can also fluctuate. So operating modes and pixel clock play a role here. Additional triggers and flash delays are provided by an FPGA counter or other channels that can be set via the software API. And an output via optocoupler can then also cause, again, a delay in the switching process of between 1 and 50 microseconds. So for more precise timing or flash and trigger, the GPIO pins are a good alternative which operate without optocouplers. Many of these delays mentioned can be measured and be subtracted from an adjustable delay. Nevertheless, a jitter remains, and which can fluctuate in microseconds range. So as you can see, the electronic circuits and components used as well as the use case and software all influence the I/O timing, which is therefore highly dependent on a camera model. So now we come to the next slide. So this is why often it is not easy to operate or expose cameras completely synchronously, especially in applications with multiple cameras, if they are configured differently, or may you also use different cameras. In such cases, it is usually a good idea to trigger only one camera, which then acts as the master and controls the exposure of the other cameras. And this allows the switching times and delays to be adjusted much more precisely using the adjustable and configurable software options. The result is a much more stable multi-camera system that delivers reproducible synchronous data. A good example of such a multi-camera application is, for example, when a 2D standard camera generates the color information for a 3D data from perhaps an Ensensor camera, a stereo vision camera. Here, the Ensensor camera is first triggered via an input, which then precisely transmits its exposure time via an output to the trigger input of the 2D UI camera. And the trigger settings are then used to start the exposure at exactly the right moment. And this allows the resulting data to be generated and combined simultaneously. Also for this topic of multi-camera and triggering IDS cameras, you can find more information in the IDS knowledge base or in our how-to video sections. But coming to another camera system or category, such as our UI XDPE with an event-based Sony sensor. I think the video should all start now. Yes. Which also have an I/O system. But this works slightly different than in image-based cameras. This is because event-based cameras do not capture images in a traditional sense. Instead, they detect only changes at pixel level, and this means they are often used in applications where very fast movements at particle level need to be detected or captured. Since the camera only provides data when something changes in the field of view, each pixel event generates represents a trigger image content combination, and this event trigger rate can be up to 100 million events per second with many changing pixels. Yeah, for example, motion paths can be captured from different angles and visualized and analyzed in 3D by triangulating identical pixel movements. As used here in a 3D volume flow analysis by the German Aerospace Center. The camera I/Os do not have to be used for an image triggering, but rather to enable the exact start of event generation and the synchronizing of multiple cameras. Here, 4 synchronized event-based IDS cameras capture tracer particles measuring 20 micrometer in a fluid flow field. And a precise synchronization is crucial to ensure that the data from the individual cameras can be merged accurately. The 4 event-based industrial cameras from IDS used for this purpose, they offer 2 particularly useful I/O interfaces. This is a trigger input that enables a unique timestamp to be placed in the data stream so that the events for 3D triangulation can be easily matched or precisely assigned to each other. And an additional hardware inhibit input allows all cameras to be started simultaneously, even if they are operated on different computers. Here, this was solved by a high-frequency pulse-width modulated signal with a 1 megahertz clock rate. Hello, let's move to another camera category. The use case is process monitoring. And this application involves less about capturing single still images with microsecond precision. Here video data is more suitable for analyzing and documenting process sequences or error situations. Cameras such as our IDS monitoring or streaming cameras generate and record video streams. This means that no images are triggered or flashed. Their inputs can be used to trigger video recordings and transfer them to a storage server, for example. And just for configuring the camera tasks, the platform-independent web front end helps you also to load, save, or delete the recordings. And here too, the input signal can be linked to various functions via camera software, similar to the standard vision software. However, since efficient video compression and keyframes are used here, trigger times accurate to microsecond are not relevant. In this demo application, the camera was connected to a light barrier via its GPIOs. The camera automatically starts recording and transfer the data to an FTP server, all without an additional PC, simply through interaction via its GPIOs. A pre-alarm time of 3 seconds and a post-alarm time of 5 seconds have been set here. And this means that in an event of rapid triggering, several files are generated that even overlap in time. This ensures that no data is lost. So that brings me to the end of my presentation. I wanted to show that I/O electronics and functional logic are separate in today's industrial cameras and can freely select and combine functions. A trigger no longer automatically means image capture, and an I/O is more than just a logic level, depending on the use case. Various camera categories with suitable I/O behavior and software are available for integrating cameras into automation systems. IDS supports you in your selection and offers many articles on I/O, flash, and trigger in our knowledge base and vision channel. Okay, for that, I would say thank you for your attention.